Hi everybody. So at the end of the lecture on types of graphs, I left you two exercises, which were finding the number of vertices, edges, and um, degrees in the in tournaments and in hypercube graphs, and also to um, determine whether a given hypercube graph is bipartite or not. Okay, so let me start by considering tournaments. For instance, let's draw a tournament of 3 vertices. Okay, so if we are given a tournament of m vertices, of course that's the number. That's the number of vertices. Okay, and if we know the number of vertices, we may not know all the different connections, because we can have something different for the same number of vertices. For instance, these two graphs are not equal. They are both tournaments of 3 vertices, but they are not equal. But we know the number of edges. We know the number of edges because if we consider each connection without the direction, then we have a complete graph. Okay? In fact, remember that we can define a tournament as a graph that has been obtained from a complete graph in which we have given direction to all the edges. So the number of edges is the same as in the case of the non-directed case, in the complete graph, in the Kn. And we know that in that case, the number of edges is n times n minus 1 divided by 2. That's the number of edges. And what's the degree? Well, the degree may depend, because remember that when we have a directed graph, we have both the in degree and the out degree. And the in degree and the out degree can be different, okay? For instance, here in this graph, we have that the out degree of this vertex is 2, but the in degree is 0. Here, the in degree and the out degrees are both 1. And here the out degree is 0, but the in degree is 2. Okay, while in this graph we can have 1, we have 1 1 in all the cases. Okay, but what we know is that for on the one hand, the in degree is always between 0 and n minus 1, and the out degree is between 0 and n minus 1, because at most we can have edges that go to all the other vertices, or edges that come from all the other vertices. Okay, and maybe we do not have edges that go out or edges that come in, like in these two cases here. But we also know that the total degree, that is the sum of the in degree and the out degree, is always n minus 1. Okay, because again, if we consider the complete graph with no directions, we know that the degree is n. So then we give direction to the edges. They either go out or in, but the total number of edges that are incident in the graph, in the vertex, are still n minus 1. Okay, so you can see here that the in degree plus the out degree is always 2, because this is a complete graph of a tournament of 3 vertices. Okay, so this answers the first question. This answers the question of whether what are the numbers of vertices, edges, and degrees in tournaments. Okay. As for cubes, for hypercubes, notice that if I have cube n, the number of vertices is, let's draw first a table. Let's try to find what is the number of vertices from a table. Okay, so qn here, and number of vertices uh, here. Okay, so for q0, remember that q0 is just a vertex. Okay, so for 0 we have 1. For Q1 we have this segment, okay, these two vertices connected one to each other, okay. So for Q1 we have 2. For Q2, which is this square, we have 4. And I guess you can easily find the next number. So for 3 we have 8, for 4 we have 16, and so on. Okay, so for n we have 2 to the power n. And this is clear because in order to define Qn, we take 2 copies of Qn minus 1. Okay, so the number of vertices is 2 times the number of vertices in the previous case. Okay, and we start with 1 and we multiply by 2 the number of vertices each time. Okay, so what about, let me go now to not the number of vertices, but the degree. Okay, what is the degree of the hypercubes of order n? Okay, so let's again consider Q0. So it's just one vertex with no edges. So the degree here is 0. Okay. Q1 has two vertices connected to each other. So Q1 has degree 1. Q2 has these 4 vertices and each vertex is connected to 2. Q3, it's the cube, and you can see that in this case the number of the degree is 3. Okay, so it's clear that for Qn the degree of each of the vertices is n. Okay, and this is so because again we start with 2 copies of the previous one. So before we connect anything with new edges, we have degree n minus 1, and then we connect one vertex to exactly another one. Okay, we connect 2 vertices of each copy of the previous graph. So we increase the degree by 1. So the degree is 1 more than in the previous case, and since we start in 0, then it's 1, 2, 3, and so on. Okay, and with this now we can determine the number of edges, okay, which is the other number that we want to obtain. Okay, so now the number of edges. Okay, so clearly in the first case is 0, in the second case is 1, in the third case is 4. Okay, so now the general rule is not so clear. Okay, but now we know the number of vertices, which is 2 to the power n, and we know the degree of each of the vertices. Okay, so if we multiply the number of vertices times the number the degree of each vertex, we obtain 2 times the number of edges. Okay, we obtain 2 times the number of edges because we are counting all the possible edges in the graph, because we are multiplying the degree, which is the number of edges in a vertex, times the number of vertices, but we are counting each edge twice because we count it in both extremes of the edge. Okay, so we obtain the number of edges multiplied by 2. Okay, so the number of edges, if you solve this equation, is 2 to the power n minus 1 times n. Okay, and this is exactly what we have here. Here n is 0, so we get 0. Here we have n1, so we have 2 to the power 1, which is 2 to the power 0, which is 1, times 1, which is 1. Here you have 2 to the power 2 minus 1, so 2 to the power 1, which is 2 times 2. Here we have 2 to the power 2 times 3, which is 12. Okay, and if you, let me do it in a different place, if you take into account the case of the hypercube of dimension 3, you see clearly that the number of edges is indeed 12. Okay, another way of getting to this conclusion is trying to solve a recursive equation. Okay, and this is the kind of thing that it's also part of discrete mathematics. Okay, and this used to be part of the course several years ago when we had two different courses, one on discrete mathematics and another one on automata theory, and then we had time to study, in addition to graphs, some combinatorics and some ideas on recursive equations and recurrence relations, which are also important for the complexity of some algorithms. But now we have no time, and we focus only on graphs. Okay, so these are the numbers in the case of the cubic of the hypercube graphs. But we have another another question that I posed to you that I wanted you to solve, which is, when are hypercube graphs bipartite? Okay, so let's start with the small cases, with the very simple cases like Q0, Q1, Q2, and see what happens. Okay, so Q0 is not bipartite. It is clear that it's not bipartite because we have not enough vertices. At least for a graph to be bipartite, at least it has to contain two vertices, okay, to have two different parts. Q1 is clearly bipartite, okay? Yes, this is clearly bipartite. Q2 is the case that we studied before. Remember that this is also what we call K22. Okay, so this is in fact bipartite, okay? What about Q3? Well, if you try to take a look at the picture of the cube in dimension 3, it's not clear whether it is bipartite or not. But you must remember the theorem that we had in order to check whether a graph is bipartite or not. Remember that I told you that from the picture sometimes it's not clear whether the graph is bipartite or not, and what you need to do is try to find if there are cycles of length of odd length or not. Okay, if there are no cycles of odd length, then the graph is bipartite. And it is very easy, it's very easy to check that there are no cycles of odd length in cubic graphs, in hypercube graphs. Why? Because we are constructing these graphs as copies of two graphs, and then we connect one copy to the other. Okay? So we can prove by induction that there are no cycles of odd length. Okay, for instance, we can start with Q0, and it's clear that there are no cycles here of odd length. This is the base case in the proof by recursion, by induction. And then we can suppose that there are no cycles of odd length in a given graph in Qn minus 1. And then when we have Qn, this is two copies of Qn minus 1. Okay? And we know by induction hypothesis that Qn minus 1 has no cycles of odd length. Okay, so in order to form a cycle of odd length, we cannot work only in one of the copies of Qn minus 1. We have to go to the other part and then return. Okay, and then you can easily see that all the cycles must be of length of even length. Okay, so these graphs are always bipartite whenever we have enough vertices for it to be bipartite. In the case Q0, it's not bipartite, but because it has no enough vertices. Okay, another way of seeing this is that if you assign coordinates to the different vertices of a hypercube graph, for instance, this one here, this is of course 0, 0, this is 0, 1, this is 1, 1, and this is 1, 0. Okay, you can assign to a hypercube, if you do it with the graph of hypercube of dimension 3, you need 3 coordinates, but you can always assign zeros and ones to the coordinates. Okay, and then if you want to have a cycle that starts in one point, for instance in 0, and goes back, notice that all the edges always go to a vertex of the graph which has exactly the same coordinates, but it's different in only one of them. Okay, so for instance here, if I move up, one coordinate changes. If I move to the left, to the right, one coordinate changes. Okay, so each time that I move in an edge, exactly one of the coordinates change from 1 to 0 or from 0 to 1. Okay, so to have a cycle, I must change the coordinates an even number of times, because I must return to the same place that I started. Okay, so I need to have exactly the same coordinates. So I change, if I move with one edge, then I need another edge to change back that coordinate. So the number of edges in any cycle on these types of graphs is going to be even, and that proves that these graphs are bipartite, even if they are, that is not apparent from the picture of the graph. If you see a cube, it's not clear at all that it is bipartite, but it is. Okay, and if you see a tesseract, a hypercube of dimension 4, it's not clear at all that it's bipartite, but it can be divided into two parts with no connections among the vertices of each of those parts. Okay, so this answers the questions that I asked you in the previous lecture. I hope that you have understood the solutions, and if you have any question related to this part of the unit or to any other of the parts that we have already covered, or to this solution, please feel free to email me or to post a question in the discussion forum. So thank you very much for your attention, and I will upload another lecture for Wednesday.